if we have a function f of xy is equal to, let's say, some z. The gradient, and we use this upside down triangle to talk about the gradient of x of f of xy is going to be a vector, and in the first component we're going to have f with respect to x, partial of f with respect to x, and then the second component we're going to have the partial of f with respect to y. Okay, so this is a vector. If we, let's say, had a function with 3 variables, so f of x, y, z, let's say equal to some w, then the gradient of f of x, y, z is going to be f with respect to x in the first component, f with respect to y in the second component, and f with respect to z in the third component. Any questions about this so far? Okay. So that's the first part over here, the definition of the gradient of f at p. So we were doing f at x and y, but if you wanted to find the gradient of f at, let's say, a comma b at some point, then that would be f with respect to x at ab and fy ab. And then in 3 dimensions, if you had 3, or really 4 dimensions, if you had 3 independent variables and 1 dependent variable, then that would be your gradient. Okay. So they give us an example. Let f of xy be x squared plus y squared. So f of x comma y is equal to x squared plus y squared. They ask us to calculate the gradient, draw several gradient vectors, and compute it at p is equal to 1, 1. So p is equal to 1, 1. Okay, so the gradient of f at xy is going to be equal to x, 2y. This is the partial with respect to x, partial with respect to y. So if we tried some different points, so let's start with the point that they ask us, the point 1, 1, and let's graph it here. So here's my x and here's my y. The point 1, 1 is here. And for the point 1, 1, the gradient of f at 1, 1 is going to be 2, 2. So it's going to be some vector pointing out like that. Okay, let's try another point. Let's try the point -1, -1. So the gradient of f at -1, -1 is going to be, so now we're here, -1, -1. The gradient is going to be -2, -2. And so it's going to be pointing in that direction. We can try a couple more points. So let's try the point -1, 1. So that would be this point over here, and the gradient of f at -1, 1 is going to be -2, 2. So it's going to be a vector pointing like that. Okay, let's try the point 1, -1. So the gradient of f at 1, -1 is going to be equal to 2, -2. That would be over here, and the gradient would be a vector like that. Any questions about this so far? So you see that these gradients, these vectors, seem to have some type of symmetrical similarity. And in fact, if we look at the function f of x, y is equal to x squared plus y squared, which was the original function, and we look at its contours, so we take, let's say, f of x, y to equal to 1, which again would mean that x squared plus y squared is equal to 1. Well, that would be a circle of radius 1. That would be the contour. And the gradient on the contour will always be orthogonal, exactly orthogonal to the screen contour. If we take another contour, x squared plus y squared is equal to 2, we get another circle, and the gradient will once again be orthogonal to this circle. And we'll see why this is soon, but that geometrically is interesting to point out. Any questions about this so far? Okay. So let's try another example, the gradient of 3 variables. So now they tell me f of x, y, z is equal to, so f of x, y, z is equal to ze 2x plus 3y. 2x plus 3y, good. And then they ask us to calculate the gradient of f at the point 3, negative 2, 4. 3, negative 2, 4. Okay, so let's first calculate the gradient of f at x, y, z. So this would be partial with respect to x, partial with respect to y, partial with respect to z, which would be equal to, so the partial of this with respect to x is going to be z e to the 2x plus 3y times 2. The partial with respect to y is going to be z e to the 2x plus 3y times 3. And the partial with respect to z is going to be e 2x plus 3y. Now we can plug in the point 3, negative 2, and 4. So the gradient of f at 3, negative 2, and 4 is going to be equal to 4 e, and then 2 times 3 is 6, plus minus 6. Okay, so 0. So this would be 4. Okay, 4. Then the next one is going to be also 4, and we would have, oh, sorry, times 2. So 8. The next time is going to be 4 times 3, which should be 12. And the last one is going to be 1. Just making sure. Yeah. Any questions about this? Okay. So the properties of the gradient, the real ones that you need to know, honestly, are the first two, because the last two, you don't really need to know them. You can just use the normal chain rule and stuff like that when you just compute the gradient. So, but the first two are fairly easy to remember. Gradient distributes into addition, and the scalar can come out. So and I'll just give an example. They say use the chain rule to find this gradient, and you don't actually have to do that. You can just compute the gradient normally. So it doesn't, and just use the chain rule when you're doing that. So g of x, y, z, g of x, y, z equal to x squared plus y squared plus z squared, x squared plus y squared plus z squared. To the 8th. So the gradient of g at x, y, z is going to be equal to g with respect to x, g with respect to y, g with respect to z, which is going to be equal to, the first one will give us 8 x squared plus y squared plus z squared to the 7th power times 2x. The second one will give us 8x squared plus y squared plus z squared 7y 2y. And the third one will give us 8x squared plus y squared plus z squared 7 times 2z. Any questions about this?
Yeah, where are you getting the 8 from?
Oh, it just comes down from here. And that gets replaced with 7, and then you do the chain rule inside.
Okay, I see. Thank you.
Okay. And that's basically what they got. They did it slightly differently, but again, you don't really need to know that. Okay. And I'm going to skip this introduction to chain rule for paths. We're not going to talk about that. So directional derivatives. When we were talking about partial derivatives, we said that this is my x, this is my y, and this is my z. And I have some surface. Then you can calculate the partial with respect to x, which would mean you take a small step in the x direction. This would be partial of x. And you want to see how that changes the z direction, partial z. And we said that the ratio, partial z with respect to partial x, is equal to f with respect to x. And over here, we would just have that this thing is z is equal to f of xy. Okay. And we also said that you can take a small step in the y direction. So this would be partial with respect to y. And that would also change something in the z direction. And we can ask the same question, partial z with respect to y. We said that would be just the partial effect with respect to y. But what happens if I want to go in that direction, in the direction of some vector? So let's draw the xy coordinate. Here's my x and here's my y. And again, until now we've done either you go in your x direction, you vary your x, or you vary your y, and you see how z changes. But now we want to vary we want to go in some direction, not in x, not in y, some other direction. What do? And we call that a directional derivative. So here's the directional derivative, and the definition is right here. So the definition of the directional derivative, we write it as directional derivative in the direction of u of f of xy. And that would be the limit as t goes to 0 of, 1 second, yeah, that's generally okay, of f of x plus, let's say, ht, x plus kt, y plus, sorry, y, minus f of x comma y, all of this over t. So we see that we're not only changing the x direction, we're not only varying the x direction, we're also varying the y direction by some proportion k and h. And we want to know what this thing is. Okay, so that's the definition, and that is right over here. Okay, so the way to compute the directional derivative is using the gradient. So we can say that the directional derivative in the direction u of f of xy is going to be equal to the gradient of f at xy dotted with u. Now u has to be the unit vector. So when we use this computation, we want to make sure that u is the unit vector. And if it's not, if they give you a u that's not, you replace it by a u that is. Let's say they give you u that whatever, the thing is equal to 3. Then you replace it by u prime, such that u prime has magnitude 1. find the unit vector. And then over here, instead of looking for that, you would look for the directional derivative in the direction of u prime of f x, y. So it's very important to only use unit vectors. So let's go back here. If f is differentiable at a point P, and u is a unit vector, then the directional derivative in the direction of u is given by the gradient of f of P dotted with u. Any questions about this? Okay. So let's do this example. Let f of x, y be x e to the y. So f x, y is equal to x e to the y. Let me actually go to a new thing because it's getting slow. Okay. F x, y is equal to x e to the y. And they want us to find the directional derivative in the direction of u of f of x, y, where u, v, so direction in the direction of v, so now v is equal to 2, 3, and p, the point where we're at, so we're going to move in this direction, and p is going to be the point 2, negative 1. 2, negative 1. So what does this mean? If we look at our coordinate system, here's my x, here's my y. On top of this, we have this surface. We are going to be at the point 2, negative 1. So we're going to be at this point. And we are going to try to move in this direction, like that. And we want to see, as you take a small step in this direction, how does z vary? How does the surface change? How does the value of our function change? Any questions about that so far? Okay. So like I said, the first thing we want to do is we want to find the unit vector of v. So let's take u is equal to v over its magnitude, which is going to be 2, 3, over the square root of 4 times 9, which is 13. So this is going to be 2 over square root of 13 and 3 over the square root of 13. So now that's going to be my u. And so we can say that the directional derivative in the direction u of f at the point 2, negative 1 is going to be equal to the gradient of f at the point 2, negative 1 dotted with 2 over the square root of 13, 3 over the square root of 13. Okay. So what is the gradient of f at 2, negative 1? So let's first look at the gradient of f at xy. That is going to be that's going to be the partial with respect to x, partial with respect to y, which is going to be, okay, the partial with respect to x is going to be e to the y, and the partial with respect to y is going to be x e to the y. So now plugging in 2 and negative 1, we get e to the negative 1, 2e to the negative 1. So these are two partials, and if let's say we were only going in one direction, then one of these would be 0 and the other one would be 1, and you would dot it, and you would just get partial with respect to x, and it would fit our previous notion of the partial derivative. But now one of these two, you don't have a 0 in one of these components and a 1 in the other. You have a partial derivative, sorry, a directional derivative. So we are going to say, once again, that the directional derivative of this at 2, negative 1 is going to be e to the negative 1, 2e to the negative 1, dotted with 2 over the square root of 13, 3 over the square root of 13. And this is going to be e to the negative 1 times 2 over the square root of 13 plus 2e to the negative 1 times 3 over the square root of 13. This is our partial derivative, which means as we vary in this direction, as we move in this direction, my z component is going to change in this way. Or we can think about this as the slope of the line, but the line in this direction above. So, so if we had here's my x, here's my y, and here's my z, and I'm at the point here, and I have a vector in this direction, and I looked at my surface above. As we vary this, the z direction over here is going to move with this proportion. In other words, if I took a plane and I cut through over here, like that, okay, not a great picture. Let's go like this, let's say. Here's my plane. Then my tangent line at this point, or at this point, will have this slope. Any questions about that? Okay, so they then ask us to do another example in 3 dimensions. It's the same thing. And then they start with properties of the gradient. And we are going to continue this next time. So next time we're going to talk about the properties of the gradient, and we're going to finish this section. Like as I said before, the gradient is perpendicular to the level curves, the contour curves of the graph. So you see all of these are perpendicular. And we will talk about why that is. And okay. And then we will stop there. So that's going to be what we do next time. Are there any questions about any of this? Okay, then let's stop here. Have a nice day.